Hello students, welcome back to OrganiChemVerse. In this video, I'm going to solve 5 questions from isomerism topic. While I discuss the questions, I will be explaining the concepts to you. So let's get started. The first question is based on the chain isomerism. There is a molecule given already. You have to find out how many of the given structure or structures are the chain isomer of the given molecule here. Students, what are chain isomers? The molecules with the same molecular formula, but the number of carbons in the principal chain will be different. That means what? You have to identify the principal chain here. Since there is a double bond as a functional group, you have to include the double bond in the longest chain. What I meant is, say, if you count from here to here, we will get the longest chain, okay? But that doesn't include both the carbons of the double bond. Hence, you cannot count the number of carbons like this. You can't count this way also because 1, 2, 3, 4, there are only 4 carbons. But if you start numbering from here, 1, 2, 3, 4, 5. Yes, this is the correct way of numbering. And in the principal chain, in the main chain, how many carbons do we have? 5 carbons. The chain isomer of this molecule must have either 4 or 6 or 7, whatever is the number of carbons, but not 5. Okay, so let's check for option A. Choose the longest chain. See, you can't count like this, okay, because it will not include both the carbons. Let's count from here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. However we do, 5 is the number of carbons in the longest chain. So this cannot be our chain isomer. Let's check for this. You can see that this is the longest chain. 1, 2, 3, 4, 5, 6 are there. Therefore, this is a chain isomer of the given molecule here. Let's count for this molecule. 1, 2, 3, 4, 5, 6. Yes, this is also correct. In fact, if you observe carefully, these two molecules are geometrical isomers. Now, let's check for the last molecule. 1, 2, 3, 4, 5, 6. So, this also has 6 carbon. If you count this way, 1, 2, 3, 4, 5, that is not correct. You have to choose the longest chain. All these 3 molecules are chain isomers of the molecule given here. And of course, for A molecule also, B, C, D are chain isomers. So, the correct options are B, C, and D. For the next question, you need to have knowledge about the IUPAC nomenclature as well as isomerism to solve this question. Choose the correct options among the given 4 options. What is the IUPAC name of this aromatic molecule? See, there are 2 nitro groups and then there is a chlorine. All of them are prefix. Because all of them are prefix, we arrange these groups according to the alphabetical priority and number in such a way that it will obey the lowest sum rule like this. Okay. If I number from here 1, 2, 3, 4, this will not obey the lowest sum rule. Therefore, the name of the molecule is 1-chloro 2,4-dinitro. Is this 1-chloro 2,4-dinitro? No. So A is not the correct answer. But look at this 1-chloro 2,4-dinitrobenzene. This is correct option. Therefore, B is the correct option. Now let's verify for C. Are these two molecules metamers? First, what are metamers? They are constitutional isomers with the same molecular formula, same functional group, but the groups across the functional group will be different. For example, ethers. Say you can have 2 ethyl group or a methyl and propyl. And secondary amines. So it can have propyl and methyl or it can have ethyl and ethyl similar to the ethers. And what else? We can even have amides and esters. You see amides, right? So here it can have a methyl like this, right? And then ethyl over here, 2 carbons, right? So they have the same molecular formula, same functional group also, right? So here also it is amide, but the groups attached across the functional group will be different. So you can see there are 2 carbons here, 1 carbon here, 1 carbon here, 2 carbons here, right? So such molecules are called as metamers. Esters do exhibit this, okay? Esters, thioethers, ethers, secondary amines, amides, all these exhibit metamerism. Now, are these two metamers? For that, let's see here. We have a tertiary butyl and methyl, and here we have methyl and tertiary butyl. The groups can be same, but the attached on both the sides it is different, right? Therefore, they are metamers. So, C is also correct. Now, the same molecules, are these constitutional isomers? Yes. Constitutional isomers are nothing but structural isomers. Yes. So, option D is also correct. Among the given compounds, which cannot show geometrical isomerism. So, there could be one or more than one molecule which cannot exhibit geometrical isomerism. So here the geometrical isomerism, we are talking specifically cis-trans isomerism. When it comes to cyclic molecules like cyclopropane, cyclobutane, cyclopentane, and cyclohexane, we can show that the molecules exhibiting geometrical isomerism using the vertical lines like this. Say if two identical groups are on the same side of the plane of the ring, then we call this as a cis molecule. If the groups are on the opposite, then it is trans. That means what? It is exhibiting cis trans, hence it can exhibit geometrical isomerism. Similarly, you can show for, say, the groups are same this time, right? So this also exhibits cis, means it will exhibit trans. For cyclopentane also you can show, say, like this. Cyclohexane, you can either show on 1, 2, 1, 3, 1, 4, whatever is the combination. Say, for example, this I can represent like this also. Easy to picturize the molecule. See here, like this. It does exhibit. But what happens if there is a double bond? But the moment you introduce a double bond over here, what happens? These two group also will be in the plane. So because of this planarity, the molecule cannot exhibit any geometrical isomerism. Say, let's assume this is this. How do you write trans? Right? You cannot write A here and then you cannot take this carbon over here. The trans is not possible, right? So that means what? It will not exhibit cis trans the moment there is a double bond. Now, let's picturize this molecule. See, here you have a double bond. You can write double bond anywhere. I prefer to write it over here. The double bond is attached to methyl like this. Okay. Then we have a methyl group over here. Suppose if I would have methyl group over here, with respect to these two, I would have done cis and trans because there is no double bond. But since the methyl is already on the double bond, it cannot exhibit cis trans. Therefore, in the cyclic molecules, if the groups are on sp3 hybridized carbon, you can do cis and trans. But if there is a cyclic and there is a double bond and there is a group on the double bond, then you cannot do cis and trans. Therefore, this molecule doesn't exhibit. This cannot exhibit, hence this is a correct answer. Now, what about this? See, the hydrogens on the double bond are not helping us to find cis-trans isomerism. But these two methyl groups, they do exhibit. How so? Look at this. This double bond is not useful, okay? But the methyl groups, because they are on sp3 hybridized carbon, right? They can be either on the same or opposite. That means what? This does exhibit the geometrical isomerism. Similarly here also, you just have to write a double bond here. But with respect to these two methyl, you can do. So this does exhibit. So this cannot be our answer. What about here? The methyl is on the double bond. So this cannot exhibit. So what is the criteria? If it is an open chain, there has to be double bond and this carbon must be attached to two different group and this also must be attached to two different group. If the identical group are on the same side, cis and trans. But if it is cyclized, then like in this case, see here exactly the same molecule, right? The group. But here it is cyclic. In that case, if the groups are same or different, it doesn't matter. It will not exhibit geometrical isomerism. Students, this is very important for the exam. Okay, please do understand this and solve some more examples based on this. Now let's solve one more question based on geometrical isomerism. This is something similar to what we have discussed. Okay, see here, the molecule is having a double bond here cannot exhibit geometrical isomerism, but the planarity of the molecule will tell us. Say if I'll take this as R group, okay? If this R group is above, hydrogen is below. What about this carbon? See, I'll take this as R group, okay? Here it is above and below. Say let's assume. That means what? With respect to hydrogen, you can say that this is above the plane, right? The hydrogen is below the plane. The bulky group is below the plane, hydrogen is above. With respect to these two hydrogen, it is trans. If it is trans, it can also exhibit cis. That means what? With respect to these two groups, it is exhibiting cis trans. Therefore, there are two geometrical isomers possible, not with the double bond. Now, we have a triple bond. Does triple bond exhibit geometrical isomerism? No, because it's a linear molecule, isn't it? Now, let's take this part. See, what is this? This is cumulene. Cumulene means what? Continuous double bond, cumulated double bond. This carbon is sp hybridized. That means what? This overall group will become linear, right? Don't assume that, okay, carbon here is sp2, therefore it will exhibit geometrical isomerism. No, that doesn't happen. See, the overall molecule is linear due to this sp hybridized carbon. Hence, you cannot do geometrical isomerism. However, students, you know that when there is a cumulated molecule, then this actually exhibit optical isomerism. But the question is about geometrical isomerism, right? Therefore, there are only two molecules, cis and trans is possible. Hence, the number of geometrical isomers are two. So let's solve the last question. This is pretty difficult and also it's quite interesting, okay? This is advanced level question. So there are some compounds given here and they are isomers. They could be either structural or stereoisomers. And there is some information about those molecules, like they could be either constitutional or they are mesomers or they have some sort of symmetry and their solution could be either optically active. You see, there are no options given here because you have to arrange the options like A matches with say 4, B with 1, C with 2 and D with 3 means what? The final number will be like 4, 1, 2, 3. So you have to answer that way. Okay, this is not the answer. You have to arrange and then come up with the final answer. Now let's take the first set of molecules. You see all of them have the same molecular formula. All of them have 4 carbons, right? There are 2 halogens. Okay, don't worry about the hydrogen. If carbon and halogens are fixed, the hydrogen supposed to be same. Are they constitutional isomers? No, they cannot be constitutional isomers because these two molecules are stereoisomers, right? Because they are diastereomers. They are non-superimposable, non-mirror images. But do they have a plane of symmetry in the molecule? Let's check that. Yes, there is a plane of symmetry, plane of symmetry, and plane of symmetry. Since all the molecules have plane of symmetry in them, can we call them as mesomers? Yes, they are mesomers. Therefore, A matches with 2. Let's check for B. So you can rule out this meso compounds one. Okay, because you have to choose only compounds with only one type of stereoisomerism. You can't choose that more than once. Okay, so you can eliminate this. Now let's check the second set of molecules. You can see that the positions of the chlorine, here it is on the cyclopropane, but here it is on this carbon, right? So obviously this and this molecule, they are constitutional isomers. In fact, they are positional isomers. Now let's check for this and this. Here also the position of the halogen is different. They are also positional isomers. And look at this. These are also positional. All three of them, they are positional isomers. And how do you categorize positional isomers? Positional isomers are nothing but constitutional isomers or structural isomers. Therefore, B will be 1. This is more appropriate. So you can rule out this also. To check for their symmetry. Do they have two-fold axis of symmetry? What do you mean by two-fold axis of symmetry? When you rotate the molecule, right? If you have to get back the same molecule again, right? So how many times do you have to rotate? Say when I rotate like this, right? Like this and then like this. So 2 times you have to rotate to get back the same molecule. Same here also, right? So we are doing it like out of plane. So when the chlorine goes here, again it should come back like this. So twofold. So this way, this direction. Same here also. When you rotate the chlorine, it comes above the plane. But when you have to make it to go below, again you have to rotate. So two times. Similarly here, right? So you have to rotate in the plane like this, right? Like this. So it is having twofold axis of symmetry. So C matches with 3. Now for the last molecule, obviously this should match with 4. Okay, you can straight away go ahead and match with 4. But however, let's verify this. See, here we have CH2Cl. This is Cl. Okay, here it is supposed to be CH2Cl. Okay, make that correction. All right. Now again we have CH2Cl and Cl. These two molecules are enantiomers, so they are going to get cancelled. But look at this molecule, still this will be there, right? So that means what? Although these two get cancelled, because we have one more molecule like this, right? It will be optically active. So that's why overall solution, although these two get cancelled, because of this, it will be optically active. So that's why D matches with 4. So I hope I made isomerism clear to you using these concepts. I have given one more question at the end of this video. Please do solve it and comment your answer. Thank you.